All right, welcome class. We're going to start this video just introducing what we're going to learn today. We're going to learn about the ideal gas law. So I think this is video number 5. We've learned about Boyle's law. We've learned about Charles' law. We've learned about Gay-Lussac's law. We've learned about the combined gas law. Today we're going to add a couple more gas laws, but going to focus on the ideal gas law. So hopefully everybody's doing well. And we have maybe 1 or 2 more videos this week, and then another worksheet. Okay, so let's get started. All right, so today's warm-up is from the previous lesson or lessons on the gas law. So I'd like you to take a minute, pause the video, try to solve, and then we'll come back and go over it. All right, so what I'm going to do is I'm going to read the problem and identify the variables that I'm given. A sample of carbon monoxide occupies 3.2 liters, okay, at 125 degrees Celsius. Those are both variables. I identified them. I underlined them. What temperature, so here's a variable, what I'm looking for, will the gas occupy with a volume of 1.54 liters if the pressure remains constant? Anything that's constant I can simply cross out. Again, pressure is not something I'm worried about. So now what I'm going to do is go ahead and list my variables. 3.2 liters is a volume. 125 degrees Celsius is the temperature, but hopefully you remembered I can't solve gas law problems with degrees Celsius, so I must convert to Kelvin. These gas laws are derived from using temperature in kelvins, so that's my first step with each of my temperatures. I add 273 if I'm going from Celsius to Kelvin. I'm also given my new volume of 1.54 liters and looking for the new temperature. So what gas law am I using? Hopefully you understand Charles' law. So there's Charles' law, and I'm looking for T2. All right, to solve for T2, it takes a little extra cross multiplying. So I move T2 up and then move T1 up and V1 down, and it ends up looking like this. V2 times T1 over V1. I plug my variables in, and I end up with an answer of 192 Kelvin. So hopefully that went well. If you're still struggling with gas laws, make sure you reach out and I can assist you with some extra practice for those. All right, today what we're going to learn about is the ideal gas law. But before we do that, I'm going to talk about one more gas law, Avogadro's law, and talk about the kinetic molecular theory, because that is kind of some major background information that you need before you move on to the ideal gas law. All right, so Avogadro's law, we've heard this name before. Hopefully, anytime I say Avogadro, you think 6.02 times 10 to the 23rd, and that's good. And we've actually learned this number before that I'm going to be using today, 22.4. So Avogadro's law is that value that we learned earlier. If I have 1 mole of any gas at STP, remember STP is 273 kelvins and 1 atmosphere pressure. So if I have 1 mole of any gas at STP, whether that be a heavy gas, a light gas, a big gas, or a small gas, if I have 1 mole, or 6.02 times 10 to the 23rd particles of that, it has a volume of 22.4 liters, no matter what gas I have. So again, 1 mole of any gas has a volume of 22.4 liters. So volume and number of moles is directly related, which I kind of think of as common sense. If I put air into a balloon, does it get bigger or smaller? Hopefully you say bigger, because I'm adding moles of a gas to that balloon. The balloon is flexible, so it increases in size. And I could graph this mathematically. I'm not going to worry about it. But what we can focus on is how does this relate to balanced chemical equations. So here's a problem. You won't see necessarily a problem like this, but I wanted to use it to further explain Avogadro's law. So ammonia burns in oxygen to form nitric oxide and water vapor. So there's my balanced chemical equation. How many volumes of nitrogen monoxide are obtained from 1 volume of ammonia at the same temperature and pressure? So to answer this question, I use that balanced chemical equation. My balanced chemical equation says 4 moles of ammonia produce 4 moles of nitrogen monoxide. Or 1 mole of ammonia produces 1 mole of nitrogen monoxide. So what I could say, because moles is directly related to volume, 1 volume of ammonia produces 1 volume of nitrogen monoxide. All right, and that is the gas laws that will help me derive my ideal gas law, which we're going to get to today. So to review our major gas laws that we've learned so far, Boyle's law, volume decreases, pressure increases, an inverse relationship between pressure and volume. If volume increases, pressure decreases. Charles' law, relating temperature and volume. If temperature decreases, so does volume. If temperature increases, so does volume. This is a direct relationship between temperature and volume. Gay-Lussac's law, temperature and pressure both decrease or both increase. Again, also a direct relationship. Avogadro's law, if I add particles, I increase the volume if that container is flexible. If I blow up a balloon, it gets bigger because I'm adding gas. So all of these gas laws can be used to derive the ideal gas law, which is going to help us solve for unknown variables when I don't have a bunch of P or a P2, a V2, a T2. It's going to help me solve for unknown variables when I have nothing to compare it to. But before we discuss or derive this ideal gas law, I first want to discuss ideal gases. So what are they? Well, you've probably heard that term before, ideal. What does ideal mean? Hopefully you're thinking, ideal, in an ideal world, we would all be in school right now. So what is that? In a perfect world, okay? But we can't be in school right now because of this virus going on. So in an ideal world, in a perfect world, gases are going to behave differently than what they actually do, okay? Right now, we're not actually in school. We're learning virtually. But in an ideal world, in a perfect world, we would be learning in school. Okay, or maybe some better way. Ideal gases are based on a perfect world. Assumptions that perfectly fit the kinetic molecular theory. Another key term for today, kinetic molecular theory. Well, kinetics, what does that mean? Kinetics, hopefully you've heard that term before, is movement. Okay, kinetics is movement. So the kinetic molecular theory is a theory trying to explain the movement of what? Molecules. So kinetics means motion or movement. Molecular, we know what a molecule is, okay? Here's a model of a water molecule. So kinetic molecular theory is a theory describing the motion of molecules. So gas laws help us to predict the behavior of gases, but they do not explain what happens to the actual molecules to cause these changes. So what we're going to try to do is explain the behavior of gases. Why do gases behave the way they do? And that's what the kinetic molecular theory is doing. All right, so the kinetic molecular theory is a theory that's not perfect, but it describes the motion of molecules, okay? So it says molecules of matter are always in motion. And we know this. Hopefully this is, again, common knowledge to us. Molecules, if I were able to look at them, they're moving. Gas molecules moving much faster and around more space than a liquid or a solid. Now, the volume of particles is essentially zero. This isn't true, but in a perfect world, we can ignore that small volume because can we actually see water molecules? If I hold up my glass of water, can I see the molecules moving around in this container? And the answer is no. Okay, so those particles are so small that when I'm doing a lot of my calculations, the volume of them isn't going to matter. So I can ignore them. Collisions of particles with the container walls exert pressure. And this is true. When a particle hits a wall, okay, or when my hand hits this wall, okay, it causes pressure. And that's what gas pressure is. It's when gas particles hit the side of a container. Particles exert no forces on each other. Now, this is not true, but the force is so weak most of the time that we can ignore it. So, and the average kinetic energy is directly proportional to temperature. If temperature increases, the energy of those molecules is going to increase as well. So this kinetic molecular theory explains the behavior of gases. Now, there's going to be some exceptions, and there's some things that aren't true about this, but it explains the behavior of gases well enough to answer a lot of the questions that we're going to be looking at today. All right, so kinetic energy, remember, we've seen this before and you'll learn a lot more about this in physics, relates the velocity and mass to kinetic energy. And the kinetic energy is totally dependent on temperature. Now, this equation allows you to calculate the kinetic energy if you know the mass and velocity. But those two are inversely related. As mass goes up, velocity goes down, and that kinetic energy is going to stay the same unless the temperature increases. Okay, so the kinetic energy of particles is the same unless the temperature increases. Bigger molecules are moving slower. Smaller molecules are moving faster, but that kinetic energy is the same. All right, so ideal gases are imaginary gases that perfectly fit all of the assumptions of this kinetic molecular theory. Okay, so we're going to pretend today, when we're using that ideal gas law, that all of our gases perfectly fit this kinetic molecular theory. Okay, so gases consist of tiny particles. Gases are in constant rapid motion. They therefore possess kinetic energy. And a lot of these are going to seem true, and they are. Okay, but there's a few pieces that aren't true. Okay, collisions between gas particles and between the walls of the container are elastic. No energy is lost. There are no forces of attraction between gas particles, no intermolecular forces. And the average kinetic energy of gas particles depend on temperature, not on the identity of the particle. So this is how we define an ideal gas, which we're going to use in our ideal gas equation. But there's a few pieces of this that simply aren't true. But we can ignore them because they don't affect our answer most of the time. So real gases do have intermolecular attractions. Real gases, when they're flying past one another, do want to stop and say hello. Okay, there are these intermolecular, remember, dipole-dipole, hydrogen bonding, London forces between molecules that pull them together. But gases are so far apart, most of the time we can ignore those forces. Real gases do have volume, although it's so small, most of the time we can ignore it. Real gases do not have elastic collisions. When they run into each other, and you'll learn about this more in physics, some energy is lost as heat. Okay, but we're going to ignore that, again, to be able to use our ideal gas equation. But in most cases, again, real gases behave very similar to ideal gases, so we can use these ideal conditions when making our calculations with a fair amount of accuracy, except there's going to be a couple conditions. If I have a low temperature and a high pressure means the particles are close to one another, so they're interacting a lot more. So the intermolecular forces start playing a major role. So this high pressure puts them closer together, and low temperature slows them down. So now if they're closer together and slowed down more, they start to interact more, and those intermolecular forces start to play more of a major role, and they're going to affect our calculations more. Also, if they're large polar molecules, they're very attracted to one another as well because they're moving slower, they're bigger, so there's a larger intermolecular force, a larger LDF force, which causes them to interact more. So in these conditions, which we're not going to worry about in this class, okay, right now anyway, might not for the rest of the year, we're not going to worry about these conditions, but in these specific conditions, our ideal gas law isn't going to work. But let's take a moment and derive our ideal gas law so we can use it. Okay? So we ended the last video with the combined gas law, which we see on the screen here, hopefully looks familiar. If I'm trying to solve for P1, V1, or T1, okay, I need my other variables. All right, so in this case, what if I don't have P2, V2, or T2? What if I don't have anything to compare it to? Well, what I can do is I can always compare to conditions at STP. Remember, at STP, pressure is 1 atmosphere, temperature is 273 Kelvin, and my volume, if I have 1 mole, would be 22.4 liters. So what I can do is I can plug those variables in and solve for variable R. And this R is going to be a constant that we use in our new gas law. But what if I change the number of moles that I'm working with? Well, what would I have to do then? I'd have to multiply this. So I'm going to add another variable from the gas law that we discussed today, Avogadro's law, that describes the number of moles, because this R is going to be multiplied by 2 if I have 2 moles, or by 3 if I have 3 moles, or by 0.5 if I have a half a mole. So what I can do is I can take that combined gas law equation, compare it to conditions at STP, call those conditions R, and then I always have something to compare it to. So this allows me to solve for unknown variables, P1, V1, T1, and now N, if I don't have a P2, a V2, and a T2. Okay? So what I have here is my ideal gas law. Typically it's rearranged and written like this, PV equals nRT. Also remembered as Pivner is kind of the abbreviated, the shortcut, the abbreviation you see in a lot of other videos. All right, so this is a note guide that I will have available for you on my website, or it is available for you on my website. You don't need to worry about filling it out, but this is what we're going to do a few example problems before we do the problems from your assigned worksheet. Okay, so in this unit, or in this week, we are going to use STP a lot, so hopefully we're comfortable with what that means. Standard temperature and pressure. A temperature of 273 kelvins, a pressure of 1 atm. Now, if I have one gas at these conditions, or 1 mole of a gas at these conditions, it's always going to have a volume of 22.4 liters. Okay. All right, so unfortunately, though, most conditions aren't at STP. So what if I'm not working at STP, but I still want to solve for an unknown pressure, volume, number of moles, or temperature? Well, then I can again compare it to conditions at STP and use the ideal gas law. The ideal gas law is PV equals nRT, and I would write that down somewhere because this is going to be the gas law that we use this week. Okay, so we're going to be solving for these variables, P standing for pressure. Now, pressure is going to be in either ATMs or kilopascals. Why? Because that's what my R is based off of. Volume is always going to be in liters because my R is based off of that as well. N is moles. R, okay, this is the constant. Now write this down because this is not going to be given to you. It's just going to be used, okay? And hopefully you've used a constant before, okay? Like if you see the symbol pi, that means 3.14. Okay, you use that number, or you can just hit the constant on your calculator. There is no R constant on our calculator, so we're going to type it in. Okay, 0.08206 or 8.31. Well, what's the difference between the two? They are dependent on the pressure that you're using. If your pressure is in ATMs, you use this R. If your pressure is in kilopascals, you use this R. Everything else is the same. So this is a constant. Write it down. Temperature is going to be in kelvins. All right, so this is the gas law I'm going to use today to solve for unknown variables. All right, so let's do example number 1. A gas is found to occupy 2.850 liters. So again, that's a variable. I like to underline it. At 22 degrees Celsius, a variable, I underline it. And 0.9737 atmospheres, a variable, I underline it. How many moles of gas are present? So my volume, my temperature, my pressure, I'm looking for N. Here is my gas law. Now, what is R? Well, again, R is dependent on pressure. My pressure is in ATMs, so I'm going to use 0.08206. And I'm sorry, this line should be right here. I must have just moved it and not moved that. So my gas law that I'm going to use is PV equals nRT, and I'm solving for N. So I rearrange this equation by moving RT over. Okay, so PV over RT. And then I plug all my variables in. My pressure, 0.9737. My volume, 2.85. R is 0.08206 because my pressure is in atmospheres and my temperature is in kelvins. So now I go ahead and solve. Okay? Here I'm solving for moles, so it ends up being 0.115 moles. My first example of using my new gas law, the ideal gas law. All right. Example number 2. a sample of CO2 with a mass of 0.250 grams. Again, I like to underline my variables that I'm given. 0.25 grams is placed in a 350 milliliter container at 400 kelvins. What is the pressure? So I label my variables, okay? Oh, I noticed something here. Grams is not one of my variables. So, can I use that to get a variable? A sample of CO2 with a mass of 0.250 grams. Well, hopefully you know or remember, I can use grams to get to moles. This is what we did in Unit 6. So I converted grams to moles, and there's one of my variables that I'm given. Next, 350 milliliters is volume, but volume must be in liters, so I need to convert. How many milliliters are there in a liter? 1,000. So I divided by 1,000, or moved it 3 places to the left to convert my volume to liters. And my temperature is 400 kelvins. I'm looking for pressure, so there is going to be how I rearrange the equation. I'm going to take V and divide it over, okay? So I have P equals nRT over V, and I'm solving for my new pressure, okay? So when I do that, I can pick which R I use, okay? Because R is used, or R relates to pressure. So if I use 0.08206, my pressure is going to be in atmospheres. If I use 8.31, my pressure is going to be in kilopascals. So I typically use 0.08206, and I find my pressure in ATMs. Make sure your answer has a unit, okay? And this is how all the units cancel out. So here's another example of ideal gas law in action, okay? Before we jump to our worksheet, and I'll make a second video going over examples from our worksheet, I want to show you quickly how you can use this equation to solve for other variables besides just pressure, volume, number of moles, and temperature. Remember, number of moles is the mass over the molar mass, or that's another way that I can get number of moles. So I can use this equation to solve for mass or molar mass if I replace N with M over MM, or mass over molar mass. If I rearrange this equation, I'm just using algebra here, I can derive a new equation, okay? And you don't need to write all of this other stuff down, but this is an equation that is worth writing down. So the two equations we're going to use on our homework are PV equals nRT, and this one right here, molar mass equals mRT over PV, where M is mass and MM is molar mass. So with those variables, I can now solve for molar mass. If you go beyond this, you might see this equation. It's another way of writing this, and it's molar mass equals density times R times T over P. And this is the same equation because density is simply mass over volume. So I'm just replacing this mass over volume with density. And an easy way to remember that is molar mass equals dirty P. Weird, but it works for a lot of students to remember this equation to solve for molar mass. All right, so let's use it quick. In the last problem, we were given all of the variables to solve for molar mass except my mass. So now I'm going to use that new equation, MM equals mRT over PV, to solve for molar mass. So my mass is 0.2509. R is 0.08206. Temperature is 400 kelvins. Pressure is 0.535. And volume is 0.350 liters. So these are just variables that were given to me in my last problem, and I use them to solve for molar mass, 44 grams per mole. Okay? All right. Hopefully that's a basic introduction, and we're going to close things out with this formative assessment problem where you're using PV equals nRT to solve for molar mass. Okay? So you take a minute and solve. All right. Calculate the molar mass of a gas If the sample weighs 3 grams, there's my mass. In a 2-liter container, there's my volume. At 25 degrees Celsius, there's my temperature, but weight, I convert to Kelvin, and a pressure of 2.294 atmospheres. So I'm solving for molar mass. So I use molar mass equals MRT over PV. So when I plug all of those in, I end up getting 16. And you could identify what that gas is if you know gases that weigh 16 grams. I don't expect you to, but CH4 does. Okay, and that would be how you would identify an unknown substance. So that was a basic introduction to the ideal gas law. We're going to do a lot more practice problems in video number 6 that's based on our worksheet.